Hey, Science 30s, and welcome to our discussion about topic 1.5 in Unit C, transmitting electrical energy. Today I want to discuss a few things. I'd like to first discuss how we calculate power. Then we're going to use power to help us calculate energy usage. And then I'm going to be discussing the role the transformers play in electrical distribution here in the province of Alberta, and for that matter, in places that have electricity all around the world. So let's start off today's discussion by discussing power, and it's a term that's used quite a bit, but by definition, power is the rate at which a device converts energy, and it's measured in watts. So when we discuss like a powerful engine, for example, how fast can a car accelerate? It has to do with how powerful the engine is. Well, how fast is that car converting uh, the energy from the engine into mechanical energy that is essentially creating acceleration for the vehicle? So that isn't that big of a stretch if you think about it when you say that power is the rate at which a device converts energy. So that kind of makes sense if you could think about it from terms of, say, a car engine. As I mentioned, power is measured in watts, which is another unit that's named after famous electrical scientist, like volts, like ohms, like coulombs. This has been a kind of a running theme throughout the unit. And power has three equations, two of which are provided in the data booklet right here. You've got power equals current times voltage. And if you take voltage, which we know is current times resistance, you can take V and substitute it for IR, which would give you IIR, which you could also show as I squared R. So you could also calculate power by squaring the current and then timesing it by the resistance in that device or that circuit or whatever. One equation that is not given to you, it is sort of given to you indirectly right here. It's the energy equals power times time. You can rearrange that equation so that power can be calculated by taking the energy that's being used by the device or the circuit and dividing it by the amount of time that it's using that energy for. So there's essentially three equations for power. P equals I times V, P equals I squared times R, or P equals energy divided by time. Again, current's going to be measured in amps, voltage will be measured in volts, resistance will be measured in ohms, energy will be measured in joules, and time will be measured in seconds because a watt essentially is a joule is a watt second, as I'll get to here when I discuss when I discuss energy in a couple of seconds. Let's go through a couple of examples in your textbook here. They are in your notes right here. Pause the video when I ask you to go over the answers as per usual. Here's what I've got. I've got volume is turned up in a car with a 4 ohm speaker, so that 4.5 amps of alternating current are flowing through the speaker. Calculate the power that's consumed by the speaker. Okay, pause me if you need to. Use one of these three equations to make it happen. Here comes the answer. Well, they've given you resistance and they've given you current, so we're going to use the I squared times R equation. In this case, we're going to multiply 4.5 amps. We're going to square that, I should say. So 4.5 squared times 4 ohms of resistance. That will give me an answer of 81 watts of power that are being used. Here's another example. Curling iron has power of 1200 watts. It's plugged into a 120 volt outlet. What's the current flowing through it? Pause me if you need to, figure out which equation you want to use. Here comes the answer. Well, I've been given voltage and I've been given power, so we're going to use this equation here. We're going to use P equals IV. If I plugged it into my equation, as you can see down here on the slide, we're going to take power is going to be 1200 watts is equal to the current times 120 volts of voltage. I'm going to take my 1200 watts divided by 120 volts. That is going to give me 10 amps in that curling iron. That's the answer for that one. Pretty straightforward stuff here. These are certainly more easier numbers to work with than what you just dealt with gravitational field strength and electrical field strength. And this actually goes back to grade 9. You would have learned this equation for sure you learned in grade 9 already. And the energy equals power times time is also an equation that dates all the way back to Science 9. I cover it with my Science 9s every year when we discuss the electrical unit in Science 9. All right, so let's discuss energy now. Energy, again, in this case, we can calculate energy by calculating the power of the device and the amount of time that device is running for. And remember, the power is equal to current times voltage. So I can also convert that equation into current times voltage times time. So that's a way to kind of expand the equation. In your data booklet, energy is only given to you with that equation there. Energy equals power times time. And but if you know this expanded version, if you know it, that P is also equal to IV, you can calculate energy just by knowing the current, the voltage, and the amount of time that the device is running. There are two different units for energy that you should be familiar with. One of them you should already know based on my discussions already. We've discussed joules already. Now, a joule essentially is calculated to be 1 watt of power being used for 1 second. So a joule is essentially 1 watt second is what a joule is. That's a good unit to use for small amounts of energy. If I'm calculating larger amounts of energy, like the ones that are being used in our homes or our businesses, we're going to need to use a different unit than joules. We're going to use something called a kilowatt hour. So we're going to calculate how many 1 kilowatt of power being used in 1 hour of time. That's essentially a kilowatt hour. And again, it's all based on that energy equals power times time equation. So let's do a couple of examples using this equation, or either one of these equations, to calculate the energy usage. Now, in some cases, these will be two-part questions. You'll have to calculate the power first before you can calculate the energy. So sometimes it'll be a two-part equation, which will be some of the equations you'll be seeing here in the next couple of minutes. Here's a pretty straightforward one. I got a light bulb that's rated for 150 watts. It's on for 8 hours. How much energy is being used? Now, there are two answers to this question based on whether you're calculating joules or whether you're calculating kilowatt hours. So pause me for a second, calculate which answer you want to go with, and I will give you the answer to both of them in about 2 seconds. All right, let's calculate joules first. Joules would be watts times seconds. So I've got 8 hours, so I'm going to have to calculate 8 hours into seconds. That's a tough thing about these equations. It's not so much the multiplication, it's the conversion. You're going to have to calculate hours to seconds, or seconds to hours, or days to hours, or seconds, or a year into days, or a year into hours. This is where the conversion, this is where the problems are going to occur in these equations, not necessarily the actual formulas themselves are pretty straightforward. So in this case, 8 hours is going to get converted into 28,800 seconds simply by multiplying 8 times 60 times 60, right? So 8 hours, 60 minutes in an hour, 60 seconds in a minute. So it'd be 8 times 60 times 60 is going to give me 28,800 seconds. I've got 150 watts. So it's going to be essentially this. If I multiply those two together, I'm going to get 4,320,000 joules. If I divide that by 1,000, I'm going to get 4,320 kilojoules. So that would be my energy use in joules. However, some of you might have done it in kilowatt hours based on what I just discussed with you on the board here. So in this case, I'm going to convert. That's actually the easier one to convert because I've already got my time in hours. All I got to do is convert 150 watts to kilowatts. So in this case, if I was converting it to kilowatt hours, it would be this conversion instead. It would be 0.15 kilowatt hours times 8 hours. That's going to give me a value of, because it's not on the slide, I'm going to have to calculate this right in front of you. I'm going to calculate this as 0.15 times 8. That's going to give me 1.2 kilowatt hours. So I have two possible answers here, depending on which units of energy I wanted to use. All right, and both of those are correct. If I didn't specify one over the other, you could calculate energy either in joules or kilowatt hours. Now, if the question specifies one over the other, then obviously you're going to need to specify for that particular unit. Let's go over another one here. I got a dishwasher that runs off of 120 volts and 20 amps. What's the power used by the dishwasher? Well, that's a pretty straightforward one. Power is going to be equal to current times voltage. So that's going to be easy. My power in this case is going to equal to 2,400 watts. Because again, it's going to be 20 amps times 120 volts is going to give me 2,400 watts, as you can see here. Now that I've got my power, now I can actually calculate my energy usage depending on how long the device is running. Well, the device in this case is running for 5 minutes. So how am I going to calculate my energy? Well, my energy is going to be in this equation here. Energy equals power times time. But again, I have to match either watts with seconds or kilowatts with hours. I can't mix and match. So I've got watts right now. I've got 5 minutes. So let me convert minutes to seconds. So 5 minutes would be 300 seconds. So if I had that in my equation, it would be 2,400 watts. Let me just make sure I got my numbers correct here. 5 minutes times 60 is 300. That's going to be 300 seconds. If I multiply those together, I'm going to basically get 720,000 joules. And again, if I divide by 1,000, I can convert that down to 720 kilojoules. However, I could have also calculated that in kilowatt hours had I wanted to. 2,400 watts would convert down to 2.4 kilowatts. And my 5 minutes, I would have to take 5 minutes and divide by 60. So 5 divided by 60 is going to give me 0.0833 repeating. And that's hours. If I multiply those two numbers together, I'm essentially going to get 0.2 kilowatt hours. So technically, both of those answers are correct. Even though in the notes it only showed you the value for joules, technically you can calculate it either in joules or kilojoules or in kilowatt hours. Again, needing to know that for my joule calculations, I need to have watts times seconds. For my kilowatt hour calculations, I need to have kilowatts times hours. Very easy to remember kilowatt hours. Joules, maybe not so much. Let's do one more. Hair dryer has a resistance of 12 ohms, 5 amps of current. What's the power used by the hair dryer? So we have to figure out which power formula we're going to use. Well, I've got current and resistance right now. So that to me smells like P equals I squared times R, which is what I'm going to use. It's going to be P equals I squared times R. If I plug all that into my equation, I'm going to have 5 amps squared. There's going to be 25 times by 12 ohms. That's going to give me power of 300 watts. And I'm going to already calculate it down to kilowatts just in case the next part of the question is asking about energy use, which guess what? It is! Go figure. How much energy is going to be used by the device in 2.5 hours? I can either calculate it in joules, I can calculate it in kilowatt hours. If I've got my joule calculation, I got 2.5 hours to seconds. It's going to be 2.5 times 60 times 60 is what I'm going to get there. 2.5, times 60 times 60. It's going to be 9,000. It's going to be 9,000 seconds. So if I do it in joules, it's going to be 300 times 9,000 seconds because it's power times time. That's going to give me 2,700,000 joules. Or if I divide it by 1,000, I'm going to get 2,700 kilojoules. That's one way to calculate it. However, I've also calculated kilowatts, and I've got it already in 2.5 hours. So my hours are already converted properly. So if I went 0.033 kilowatts times 2.5 hours, last time I checked, that's going to be, I'm going to guess 0.75 kilowatt hours, and you can double check the math for me on that, but I'm pretty sure it's 0.75 kilowatt hours if my math is in fact correct. So there you go, a couple of different answers there depending on what you're going to do. And again, reminder, 2 different units for energy, joules for small amounts of energy, kilowatt hours for larger amounts of energy. Understand that joules, again, bottom of the slide here, very important. Joules are watts seconds, whereas kilowatt hours are kilowatt hours, which again, you can't really get kilowatt hours wrong because it tells you what the power and the time unit are. You just got to remember the joules are watt seconds. And if you remember that, the calculations are pretty straightforward. And by the way, when we're calculating energy, we're also calculating energy usage. That allows us to calculate stuff like in our energy bills. And they are energy bills. They are not power bills. I mean, a lot of people call them power bills. But we are calculating the amount of energy we're using in our house, not the amount of power. However, there is a correlation between energy and power because the more powerful a device is, the more energy it will be able to convert and how much it's going to use, right? So, but technically, strictly speaking, we are measuring the kilowatt hours that are used by a house on a monthly basis, that is the breakdown for an energy bill. And again, they're not power bills; they're energy bills because they are measured in kilowatt hours. We're not giving you an energy bill. So even I did it. An energy bill comes in kilowatt hours, not kilowatts. So that's why they're energy bills. But can we calculate how much an energy bill would be? Well, if we know how much energy we're using in a home in kilowatt hours, and we can calculate what the kilowatt hour rate is from the utility company, we can calculate the amount that we're going to have to pay. So there's a question on the bottom here, which is exactly the same as the question up here on the slide. Let's see if we can calculate this. I've got the cost of electricity. I've got a TV that's in standby mode, which means it's plugged in. It's not on. It's just in a standby mode. It's going to use 8 watts of power over a period of a year. What would the cost be to the consumer if they're paying 9.3 cents per kilowatt hour? Okay, well, I know that I need to calculate my energy for this, which is going to be power times time. I've got my 8 watts, but I've also got a time of a year. And I need to convert this. This one I need to convert into kilowatt hours because my usage rate is in kilowatt hours. It's not indicating how much I'm paying per joule. It's telling me how much I'm paying per kilowatt hour. So in this case, I have to calculate my energy in kilowatt hours. So my watts have to first be converted to kilowatts. So my watts are going to be 0.008 kilowatts because that's my power. And then my time, I have to convert years into hours. Well, I know there are 360, so 1 year is going to be equal to 365 days. So that's my number of days. Each day has how many hours? Well, 24. So 365 times 24 is going to give me 8,760 hours. So that's going to give me my number of hours. So now I've got my number of hours plus my number of kilowatts. That's going to tell me how much energy that TV is going to use in standby mode over a period of a year, which works out to 70.1 kilowatt hours. But that isn't the answer to the question. The question is asking me how much would I be paying if I'm paying 93 cents per kilowatt hour. So now all I need to do is take 70.1 and multiply it by 9.3 cents, which I need to convert to dollars. So it's going to be 0.093 is going to be my dollar value in a percent or in a decimal form. So if I convert that to dollars, it's going to be 70.1 times 0.093. It's going to give me an answer of roughly $6.52, which is what you see on that TV right there. So that's how you calculate an energy bill based on knowing the power of the device, how long it's been on. You find out how much energy it's using in kilowatt hours, figure out the rate per kilowatt hour, and then just multiply by the rate per kilowatt hour, and you got yourself your power bill, or your energy bill, because it's not a power bill. I keep saying that because, hey man, it's entrenched in this old brain of mine. So speaking of energy bills, consumers do not want to pay extra for utilities, and you're going to be there very soon. You're going to be paying your own bills at some point here for your own power and your own gas and all that stuff. So electrical companies have done what they can to minimize the loss of electricity through transmission. And that's very important because if they were losing a lot of electricity before it got to your home, they would build that into the price per kilowatt hour so that you'd be paying for electricity that didn't even get to your house if they couldn't deliver the electricity efficiently. We've discussed how this happens sort of roundabout when we discuss motors and generators. I discussed to you at that point the difference between an AC and a DC current, or an AC and a DC generator. AC being alternating current, DC being direct current. And this was the whole battle that was raging between Tesla and Edison. If you didn't watch that video in the motors and generators lesson, maybe watch that video now, because it does discuss sort of the difference between AC and DC current and why we need one or the other. We still use both of them today. DC current is very good for batteries, for devices that are powered by battery. A lot of the portable electronic devices that we're using in our homes today are DC circuits, or they have DC power in them, or electricity. But to get the electricity to your house, we're going to use alternating current. And the reason why, and this was Tesla's invention. Tesla came up with AC, and remember Edison came up with DC. Long distance transportation, AC allows us to have very little electrical loss. And the reason why is that if we have AC current in our electricity when we transmit it. So if I'm transmitting electricity from the Genesee power plant in Wabamun out here to Morinville, that's tens of kilometers. That's like probably 60 some kilometers, 70 kilometers away to transmit that electricity out to Morinville. We don't want to have a lot of resistance in the line. So what we do is we basically we play around with the energy, the electrical energy that's actually in the circuit. We're gonna play around with it by bumping up the voltage. By increasing the voltage, we can then decrease the amount of current, and we're able to get less problems in the way of resistance. With a smaller current, there's less of a possibility of that current being kind of kiboshed by any kind of resistance that's in the line. Voltage doesn't get affected by resistance. Current does. So if we can increase the voltage and decrease the current, that's a good thing. And we can't do that with DC. We can only do that with AC. And the device that will allow us to do that is called a transformer. A transformer will essentially convert electrical energy and will either step up or step down the voltage in an electrical line. And you can only do this if you're using AC transmission. You can't do it if you're using DC transmission. It will only work with the AC. So that's why we use AC for electrical transmission. If you watch that video about Tesla and Edison, you saw the whole thing about Edison had all those power plants that had to be like 2 kilometers away from each other because he would lose signal. We don't need to do that using AC with Tesla's version of electrical transmission. So what is a transformer? Well, a transformer, and you know what a transformer are because they're all around town. If you see those big square boxes that have those wraparounds that have the provincial parks wraparound, they have like pictures of waterfalls and mountains on them, those green boxes are essentially, they are basically step-down transformers that are taking the high voltage that's coming in from the transmission lines and stepping it down to a lower voltage that's safer to be brought into our homes. But that's an example of what a transformer is. Now, what does a transformer do? Well, a transformer takes a circuit that comes into the transformer, and it takes the AC voltage that's on that circuit, and it will convert it to a different voltage on a circuit that's leaving the transformer. So essentially, one circuit comes in at a specific voltage, then at the other side of the transformer, another circuit will exit with a different voltage, either a higher or a lower voltage, depending on whether we want to step down the voltage or if we want to step up the voltage. And I'll get to the differences between that in a couple of seconds. How do we do this? We use a magnetic field. We use electromagnetic induction all the way back to Faraday. This goes back to Faraday's models back in the 1800s that allowed us to basically create motors. Well, here's another application of Faraday's electromagnetic induction, basically using that magnetic field to generate an electrical current. And we just basically take one electrical current, convert it into another, and it's all electricity. We're not dealing with electricity being converted to another form of energy like you would see in a load resistor. This is essentially taking all the energy that comes in, that's all electrical energy, and all that electrical energy leaves. Now, how does that happen? Well, you understand that energy, back to our equations from today, energy is equal to power times time. Well, the time is not really a factor because the time will be the same for both of the circuits that are inside the transformer. So essentially, in this case, energy is equal to power. Well, what's power made of? Well, power, as you know, is current times voltage. So if I adjust the voltage, if I take the voltage and make it higher, to compensate, the current is going to go down. If I decrease the voltage, then my current is going to go up. I'm not losing any of the energy. I'm just sort of rearranging the distribution of the energy in the circuit. Some of it, more of it is either voltage or more of it becomes current, depending on what the transformer is doing. Now, like I said, when we're distributing electricity down the line through transmission, we want high voltage. We want high voltage and very low current, because with not much current in the line, there's not as much of a problem with resistance, because remember, resistance is kind of trying to stop current. Resistance doesn't really affect voltage per se. So if I have high voltage and low current, That's a great way to transmit electricity. But when I generate the electricity initially in the power plant with a generator, that generator will have it at a higher current and a lower voltage. So then I'm going to have to step up the voltage in order to transmit it. So in that case, I'll need what's called a step-up transformer. That high voltage transmission will go to, say, a town like Morinville. And then when it gets into Morinville, I have to step down the voltage using a step-down transformer to bring the voltage down to a lower level, a safer level, and to increase the current as a result. So that's what these transformers are doing. And depending on what we needed to do, I'm going to explain what both of these transformers do in a couple of seconds. But let me first of all just give you the general rundown of what a transformer is. Transformer is going to have a primary and a secondary coil on it. The primary coil is the input circuit. That's where the electricity is coming into the transformer. The secondary coil is where the electricity is leaving the transformer. There is no direct contact between the primary and the secondary circuit or coils. What's happening is you've got a magnetic field that is basically transferring the electricity from one circuit to the other. But what we do is we wrap various amounts of the coil on either side of the transformer. And depending on whether I have more coils to start and less to end with, or less to start with and more to end with, I'm either going to step down my voltage or I'm going to step up my voltage through that process. So that's sort of what a transformer generically looks like. And as you can see, the power and also, i.e. the energy or the power coming in is going to be equal to the energy or the power coming out of this transformer. What's going to change is going to be my ratio of I to V. If I increase my voltage, then by default, my current will have to drop. If I increase my current, my voltage will have to drop in order to maintain the same energy level. And again, this is like the second law. This is the first law of thermodynamics. You can't create or destroy energy, right? You can only transform it. And in this case, we're not transforming electrical energy to another form of energy. We're just converting the breakup of the electrical energy inside the circuit. What percentage is going to be the current and what percentage is going to be the voltage to determine what we need at a given point. If it's transmission, we need lots of voltage and little current. If we need it in our homes, we need less voltage and more current. That's what we need. And I'll explain how both of these work here in a couple of seconds. Now, while you don't need to know the exact physics behind a transformer, you do need to know how to calculate the new voltage and current that's produced by either a step-down or a step-up transformer. And that's what I'm going to get to right now. To do this, go to your data booklet on page 3, and you're going to go to right to here, I think. Nope, right there. Ideal transformers. Those are the formulas you need right there, and they are listed on the top of the next several pages in your notes. They're there. So what we've got there is these are our formulas. I've got NPNS equals VPVS, and I've got MPNS equals ISIP, and then I've got VPVS equals ISIP. Whew, what does that mean? Well, here's what it means. NP refers to the number of coils on the primary circuit or the primary coil. NS refers to the number of coils that are located on the secondary circuit or the secondary coils of the transformer. VP is the voltage of the circuit, of the primary circuit that's coming in. So in this case, this would be VP over here. VP would be 500 volts. In the case of IS and IP, same idea. IS is going to be the current on the secondary coil, and this is going to be that's going to be my IP. So right now I've got so I'm just going to maybe make a note of these. So right here, this is going to be my VP. This is going to be my IP, because that's my current. That's my current on the initial coil. That's my voltage on the initial coil. Now, what's my NP on the initial coil? Well, I'm going to count my number of coils. 1, 2, 3, 4, 5, 6, 7, 8. So my NP over here is going to be equal to 8. On the other side, I've got not 8 turns, I've got 4 turns. So I've got a number of NS equals 4. So basically what I'm saying here is 8 over 4 is going to be equal in this case to 500 over Vs. So it's just basically a ratio. So just to kind of show what I'm doing here. So in this case, for this transformer, I'm going 8 over 4, which would be my NP over my NS, is equal to my VP, which in this case is 500 volts, over my mystery variable, which is underneath. Well, if you use cross multiplication there, that's going to be 500 times 4 is 2,000. 2,000 divided by 8 is going to be 250. So I can calculate that on this side of the transformer, I have now stepped down my voltage from 500. I've stepped down my voltage from 500 to 250. It's essentially a ratio. If I've got twice as many coils on my primary side that I have on my secondary side, that's going to decrease my voltage by half. The higher side of coils, and if I go to a lower side of coils that's a step down transformer because I'm going from a higher number of coils to a lower number of coils, it's going to decrease my voltage. Now I know that if I decrease my voltage to compensate, my current's going to have to increase. That's why here in the equation, NP over NS is equal to IS over IP, because there's an inverse relationship. If I decrease the number of turns from my primary to secondary, my current's not going to go down. My current's actually going to go up. And in fact, my current is going to double because I'm going from 8 over 4 is essentially going to, in this case, and let me just move my numbers over here. So here's my IP over here, which is 2 amps. I know my NP is 8. My NS is 4. My IP is going to be 2 on the bottom, is going to be 2 amps. So in this case, I have my variable on the top, which I don't know, which is my current on my secondary coil. So I'm going to take 8 times 2 is 16 divided by 4. That should give me a variable of 4 amps. Now let's confirm our numbers here. I said that we had 1,000 watts of power on the primary coil. 500 times 200, 5 times 200 is going to give me 1,000. I times V, right? What about my secondary coil? I got 250 volts times 4 amps is also going to be equal to 1,000 watts of power. There's the conversion. So this would be an example of a transformer in Morinville that's taking the high voltage coming into town, and we're stepping it down to a lower voltage. It's going to be safer for us to use in our houses and our homes. That would be the example of a step-down transformer. Here's what I'd like you to do right now. Now that I've done that, I would like you to go over to our next transformer, which is here. Oh, by the way, before I do that, watch this video. Watch this video on transformers. That might give you a better idea before we tackle the next part of this board. Watch the video. Now I'm going to give you, and I've also got other stuff here. Here's some examples. These are some other examples that are slightly different than the ones I've got on the board, but they're the same idea. Step-down transformers versus step-up transformers, and they're giving you the numbers that match up. This one's got 50 coils or 50 turns on the primary coil. You've got 10 turns on the secondary coil. That's a ratio of 5 to 1. Well, you can see my voltage is going from 1,000 to 200. That's a drop of 5 times. And then my amps are going up 5 times from 2 to 10. So it's basically just a ratio thing that's going on. This is actually quite straightforward once you figure out how to do it. But let me give you an example now that I want you to plug away at. I've got a step-up coil now, all right? I got a step-up coil that has 2 turns on the primary coil. I've got 10 turns on the secondary coil. So I've got 2 turns going to 5 turns. We're going step up. Less coils to more coils. On the primary circuit, I've got the same amount of voltage that I had on the other one. I had 500 volts and 2 amps. So a total of 1,000 watts of power. What I want you to calculate is this is a step-up transformer. Pause me and see if you can calculate what the new voltage and the new current are going to be on the secondary circuit. See if you can figure that one out, and I'm going to give you the answer here right away. Here's what we're going to do. We're going to use our formula. I know that my NP over NS ratio in this case is going to be 10 over 2. 2 turns is my NP number. 10 turns is my NS number. And then I know that's going to be equal to my current, my primary voltage, which is 500 volts. And then I have to calculate my secondary voltage. Okay, So I got 500 over Vs equals 2 over 10. 500 times 10 is going to be 5,000. Divided by 2 is going to give me 2,500 volts. 2,500 volts. That's what I've got so far. All right. Now, what about my current? Well, my current's going to be secondary, which I don't know. So IS over IP, and I do know my IP number is 2 amps. So I've got 2 over 10 now equals IS divided by 2 amps. So if I take 2 times 2 is 4 divided by 10 is going to be 0.25. I think I did that right. No, that's not right. Hold please. I want to make sure I'm not giving you erroneous numbers here. 0.4, pardon me, it's 0.4. 0.4 amps. 0.4 amps is going to be my amps on my secondary coil. Now, how can I check my work on this? It's very easy. In theory, these numbers multiplied together should be equal to these numbers multiplied together over here. I got 500 times 2 is going to give me 1,000 watts. What's 2,500 times 0.4? I'm going to guess that it's 1,000. Bam, 1,000. That's the check. So on these questions, you can easily check your work by just making sure that the overall power using the power times current times power equals current times voltage, multiply both sides together to make sure, check each side to make sure that they give you the same number of watts. Because if the watts have changed, you've done something wrong. But that's basically how step-up and step-down transformers work. Here's another example of a step-up transformer. This one has got a 5 to 20, so it's got a 1 to 4 ratio on the step-up. So my voltage is going to increase by 4 times. It goes from 100 to 400, as you saw, and then my current dropped by 4 times. I just fell off that slide there. Let's do a quick question here. I'm going to erase some of this stuff to give me some room to work, because heaven forbid I need to work on this board here a little bit. $5 says I'm going to knock the board off. Okay. Let me get all my equations back up here. Okay. Here's what I've got. I've got a neon sign requires 12,000 volts to run. It operates off of a 220 volt receptacle. It has a transformer with 10,000 turns on the primary coil. Okay. So is it going to be a step up or a step down transformer? Okay. So I know that my output needs to be 12,000 volts. My input is 220 volts. So my voltage is actually increasing. It's stepping up. My voltage is what we determine. Remember, the coils are proportional to the voltage. So if the voltage is going up, my coils are also going up on the secondary coil. So this is definitely going to be a step-up transformer. This is definitely going to be a step-up transformer. No question whatsoever, because the voltage is increasing. We know it's a step-up transformer. What's the number of turns on the secondary coil? Here's where things get interesting. So I said that on the primary coil, there is 10,000 turns on the primary coil. So my NP number is going to be 10,000. My VP number, because it's my starting voltage, is going to be 220 volts. And my VS number is going to be 12,000. So I'm going to plug this into my equation right here. NP over NS equals VP over VS. So I'm going to do this. 12,000 volts over 220 volts is going to be equal to 10,000 turns divided by the number of coils on the secondary coil. So I'm going to use some math for this. Going to do some cross multiplication. I got 10,000 times 220 divided by 12,000. I should have, Have I done this wrong? I did something wrong here. This is how easy it is to mess up, okay? You're all at home yelling at me going, no, you got your numbers wrong. I did get my numbers wrong. Let me run this by you again. That's what I did wrong. No, I didn't do anything wrong. You know what's wrong? My notes are wrong. My notes are wrong. Let me explain this to you. This is the lovely thing about live television. First time I've actually, this is only the second time I've used these notes. So let me explain what's happening. This will not be wrong on your end. So let me explain what's happened here. Let me just confirm all this. I've got 12,000 is my secondary voltage. It's the one that's leaving the receptacle. 12,000 volts are leaving the transformer. Entering the transformer, 220 volts. That's my primary voltage coming in on the initial circuit. Now, the question is clearly saying that there are 10,000 turns on the primary coil. So that is in fact correct. So I'm going to go with 10,000, which is going to be my NP number, is going to be over NS. My VP number is going to be 220. My NS number, my VS number is going to be 12,000. That's my cross multiplication right there. So you know what? Apparently I just didn't know what I was doing there, because apparently this is going to work now. I can see the numbers are going to work already. I must have done something wrong there. Live television, isn't it great? So I'm going to multiply these two together, which is going to give me 120 million. I just multiplied 10,000 times 12,000. I'm going to divide that by 220 now. That's going to give me the number that's actually on your notes. So my notes aren't wrong. I just somehow made it count. I don't even know what I did. I just mixed up the numbers there. But it's very important that you're not mixing them up, because apparently if I can mix it up, so can the best of them. It is actually pretty straightforward though. If you have any other questions about it, please contact me in class. I kind of boggled that one up a little bit, but the ones before this certainly were all correct. I know the ones before this were all correct. I just sort of got caught in my own hubris, thinking I could do it without paying attention. Apparently, time for me to retire. That's okay. All right, a couple more things before I'm done. Modern electricity transmission relies heavily on transformers. I talked to you about this already. High voltage electricity is produced at a power plant. For example, it's going to be up to maybe 12 kilovolts in the circuit. But then we're going to step that sucker up. So when we go from the power plant to the transmission lines, we're going to use step-up transformers. And you should know this. You could get a question where you're actually asked to know where a step-up or a step-down transformer is going to be located. Step-up transformer is going to be from the transmission source to the transmission lines. Then when the transmission lines have the high voltage and the low current, we're then going to step it down before it goes into the communities. You'll have a step-down transformer substation that's going to bring it down to a reasonable level, so then the power lines in a town are not going to have quite as high. And then you're going to have your transformer boxes that are literally right before they enter the homes. So you're going to have step up going to transmission, and then step down going towards your homes. And again, take a look at that slide. It kind of narrows it out for you a little bit, but you should sort of know where step up and step down transformers are. Well, now that I completely boggled the end of that, otherwise what I thought was a stellar performance, here are the questions for your recovery on this topic, and it's the last one for this half of the unit. Complete questions 39, 42, 43, 46, 50, 51 on pages 387 to 402, and then I'm going to get you to do questions 1, 2, 4, 5, 6, 7, and 8A on page 403. That is it for the first half of the electromagnetic energy unit. Coming up next time, we are going to start delving into the electromagnetic spectrum, discussing a little bit about astronomy, and even a little bit about this guy right here, Monsieur Albert Einstein, and his very famous equation, E equals mc squared What was it all about? It's about the speed of light, energy, and mass. And you know what? You can't have mass if you're traveling at the speed of light. I'll be discussing why that can't happen and why we can't travel at warp speed, all coming up. Second half of this unit. Thanks for tuning in, everybody, and we will see you real soon.